Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will look at fallacious proofs. So basically a proof is a flawless argument. It is a set of statements in which none of them can be refuted. Now these statements or premises, they need to follow one another in mathematics. So you'll have a statement and then you'll deduce something from that statement and you'll keep following that process until you reach a conclusion. Now mathematics is alone in that it is the only subject in which you can prove something. Even in other areas of science, the best you can really do is say that something happens most of the time. But before we learn to construct our own proofs, we're going to look at fallacious proofs. They're proofs that are invalid because of a logical flaw. So here is an attempted proof, that's why I put it in quotation marks, that any number divided by itself is equal to 1. So we start off with this number a. Now it's obviously true that 1 times a is equal to 1 times a. That's not a problem. But what I've done to go from here to here is I've divided each side, this side and this side, by 1 times a. So then, of course, 1 times a divided by itself presumably equals 1. And then on this side, I've done 1 times a divided by itself. Now, here's the problem. I've used what I was trying to prove. I've used this, which is the proposition, to prove the proposition. So that's a bit of circular logic. I can only deduce this here because I have assumed that any number divided by itself is equal to 1. So that's called circular reasoning, and that leads to a fallacious proof. It's almost like saying this shape is a square because it is a square. Doesn't make logical sense. Now, a problem with the proposition, the original statement that we want to prove, is that it's actually not quite true. Can any number divided by itself be equal to 1? Well, almost. But what about 0? I need to update this. It turns out that any non-zero number divided by itself is equal to 1. And that's really important for when we're doing proofs in maths. See, sometimes things are talked about as being like proved beyond a reasonable doubt, say in the legal system, but in maths, we're very precise with our proofs. If there is just one case in which it doesn't follow, if you have a rule and there's one exception to the rule, that needs to be clearly stated. So if I was going to prove this, I would need to stipulate that a does not equal 0, and then I would need to go about proving it. But again, I've come down to a over a equals 1. Well, that's precisely what I was trying to prove. I can't use what I'm trying to prove as evidence for proving it. That doesn't make any sense. So let's look more at some fallacious proofs. So here I have a very short proof. Again, proof is in quotation marks because this proof is totally fallacious. I've said that all even numbers are prime. So here, the idea is because 2 is prime, that means every even number is prime. And this is obviously untrue. This is actually so obvious in this particular example, but it happens a lot by people in mathematics. They think if something works once, that means it always works. And that is never okay. That is a logical fallacy. Just because 2 is prime, it doesn't mean that all other even numbers are prime. In fact, it doesn't mean that any other even numbers are prime. And we know that. We know every other even number is actually not prime. So even though that sounds like a very obvious example, please make sure when you're constructing a proof, you never assume that something is always true because it's true once. So here we have a harder example. Again, this is a fallacious proof that 2 equals 1. If anyone ever tells you they can prove that 2 equals 1, you should be immediately suspicious because it's just not true. Now, a lot of people look at this proof and think it's valid because the fallacy here is actually quite subtle. So let's start off with it. So let's let a equal b. A and b are just arbitrary numbers. So then what I've done to get from here to here is I've timesed each side by a. A squared equals ab. That's fine. Nothing wrong with that. Now, from this side and this side, I've subtracted b squared. Again, that's fine. I'm balancing the equations. Each step follows from the previous step because I'm balancing the equations, because what I do to one side, I'm doing to the other side. So we're really good up to here now. So then I factorize this. So you know from other areas of mathematics that a squared minus b squared always equals a minus b times a plus b. No exceptions to that. So again, on the other side, I've factorized. Here I've used highest common factor. There's nothing wrong with this line. This is all true, and we know that from other areas of maths. Now, the problem is, if I go from this side to this side, what I've done to both sides of the equation is I have divided by a minus b. So as we saw in the previous slide, this can cause a problem if the thing you're dividing by could equal 0. And in fact, if a does equal b, it doesn't matter what the values of a and b are, a minus b will equal 0. So in fact, to go from here to here, I've essentially divided by or cancelled 0. And that means that all subsequent steps are incorrect because they follow a premise that is logically flawed. See, essentially, this proof basically says that 2 times 0 equals 1 times 0, and therefore 2 equals 1. To go from here to here is a logical fallacy because we can't divide each side by 0. So just this one wrong thing here by not considering that a minus b was 0, just that one wrong line makes the whole proof invalid. It is a fallacious proof, and therefore the conclusion here, 2 equals 1, cannot be trusted. And of course we know 2 can never equal 1. Alright, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.